It's a question of Ramanujan. Write this nested cube root as the sum of the cube roots of x, y, and z, where x, y, and z are rational numbers. Again, before solving this myself with Galois theory, I'd only ever seen Olympiad solutions to it. They would start with this unrelated number and cube it, binomial expanding to give this, canceling the cube root and combining. Then on one side we multiply and divide by cube root of 4 minus the cube root of 2 plus 1, all cubed. And on the other side we multiply and divide by the cube root of 2 minus 1. Expanding these out and canceling, we see why we did that, the geometric sum canceling down. Then we invert and cancel one of the factors of 3, take the cube root, and combine. So x, y, and z are 4/9, -2/9, and 1/9 in any order. But again, that's enough for an Olympiad because it's a solid proof, but it has no scaffolding to tell us how it got solved, or how we should solve other similar questions. Where the hell did the 3's come from? Why do the roots look so similar, but the 2/9 is negative? In this section, we're going to expose the scaffolding behind this question. So just as before, we have a 5-element agenda. First, take the left-hand side and compute its minimal polynomial. Use its equality with the right side to compute the Galois group. Next, study the roots of the minimal polynomial, including writing down obvious redundancies. Third, we look at the Galois group, which we discovered from the right-hand side, and look at it as acting on the roots similar to the left-hand side. We'll have a full accounting of the Galois group as permutations of the 9 roots. Fourth, with that accounting, we're able to detect hidden redundancies in the same way we did in the last example, and thereby eliminate spurious transformations of the roots. And finally, we collect those redundancies to find the answer. This is the step that took the most time in the previous question, but it'll be easy here. The first step is to write down the minimal polynomial and Galois group. If we let x equal the left-hand side, we can do a couple of manipulations to turn it into a polynomial with only rational coefficients. Here's the end result. Remember, we need to work with irreducible polynomials or else the roots don't mix. So is this irreducible? Spoiler, yes, it is, and we'll use Eisenstein's criterion mod 3 to prove it. Taking it mod 3, the middle terms cancel, and 9 equals 3 times 3, and remembering the Frobenius automorphism twice, we end with x minus 1 to the 9th mod 3. And hence if we instead look at p of x plus 1 mod 3, the end result is x to the 9th. So all the coefficients below the leading term are divisible by 3. The other half of Eisenstein is to know that the constant term isn't divisible by 3 squared. And we know the constant term is when we plug in x equals 0. That's p of 1, which ends up just being 6. Obviously not divisible by 9. So Eisenstein says it certainly is irreducible. That's great, because that means that the Galois group can map each root to each other root, and this is in fact the minimal polynomial. Amazing! Now let's figure out the Galois group. If L is the splitting field, we know a few things. First, if x satisfies this equation, then zeta 3 times x does too, since x is only being cubed. So zeta 3 is the ratio of 2 roots and must be in L. Second, on the right side of the equation, the Galois conjugates of the cube root of x are the cube root of x times a power of zeta 3. That means that if M is the field generated by zeta 3 and the cube roots of x, y, and z, then M contains all the roots, so the splitting field L sits inside M. It might be equal to M, it might not, but L certainly must at least sit inside M. And finally, we know that M is Galois over Q. Why? Because it's built from 3 Galois extensions, the splitting fields of t cubed minus x minus y and minus z. And any Galois action of M can be built from permutations of these 3 fields, which means that their images all land back in M. In other words, any irreducible polynomial with one root in M is built from these 4 components, zeta and the cube roots, and hence we can write down a polynomial whose roots are given by applying the Galois groups of root x, root y, root z, and zeta 3 separately, and this polynomial has rational coefficients, so it's divisible by that irreducible polynomial, and hence its roots are all in M also. Great! So what is M's Galois group? Knowing this will help us figure out what L's is, but M is easier to analyze. Anyway, so what do we know about M? It contains zeta 3, and everything else is essentially symmetric, so let's look at the Galois group of M over Q adjoint zeta 3. Because we know the Galois groups of the cube roots, we can combine them to say that a permutation of M that fixes zeta 3 is explicitly given by what it does to them. The Galois groups being multiplication by some power of zeta 3, everything is determined by which power of zeta 3 it multiplies each of the cube roots by. So we can write down the Galois elements sigma sub u v w, where sigma multiplies root x by zeta to the u, multiplies root y by zeta to the v, and multiplies root z by zeta to the w. Of course, not all of these need to be actual Galois elements. There might be some interconnectedness between x, y, and z, but every Galois element that fixes zeta 3 is exactly one of these. And we care because we'll show that they all commute. Writing down the product of two of them, it acts on root x, and we know how the inner one acts on the cube root of x via zeta to the u2, which we can pull out. And again, the inner one acts by multiplication by zeta 3 to the u1. We combine powers of zeta 3 and see that this is symmetric in u1 and u2, and so we can actually reverse the order of the two. Similar computations with root y and root z prove the same thing, so any two sigmas actually commute. And of course, each is of order 3 since we're multiplying by powers of zeta, which repeats after 3 steps. So as an abstract group, gal of m over q adjoint zeta 3 is contained in z mod 3z cubed, the inclusion map being sending sigma uvw to uvw. Told you m was easy. And now looking at the Galois group of L over q adjoint zeta 3, it's a quotient of gal of m over zeta 3 by forgetting about how the Galois elements of M act on anything outside of L. So it is also abelian. Everything commutes here too, with elements of order 3 and the identity. And it has at least 9 elements because we have to be able to take every root to every other, so it has to be either z mod 3z squared or cubed. Which one? Well, if it had 27 elements, there being only 9 roots of p, each root has to be fixed by something. But how can the cube root of x plus the cube root of y plus the cube root of z be fixed? Back inside M, the claim is that if a Galois element fixed the sum, then it has to fix each component piece. Why? Well, it might feel obvious, but to prove it, we use this cool piece of math called the reduced trace, TR, that can pick out the cube root of x component from the sum, and hence can detect whether the cube root of x component updated, and similarly for y and z. I won't go into that more than that, but you can read the proof written here. And so if that's true, then any Galois element of M that fixes the cube root sum fixes each piece individually, and also fixes zeta 3. So it actually fixes every conjugate of the cube root sum, and hence is the identity. So we know that the only Galois element that fixes anything is the identity, and so the Galois group can't be z mod 3z cubed, so it must be z mod 3z squared. But we should eventually worry about gal of L over Q instead of over Q adjoint zeta 3, but it has this order 9 subgroup, and its quotient is the Galois group of zeta 3 over Q, which is a quadratic field, so it has order 2. So gal of L over Q is a group of order 18, and we'll worry about its structure later. That's good enough for now. Great, that's one step of 5 down. Recall step 2. Analyze the roots of this minimal polynomial x to the 9th plus 3x to the 6th plus 3x cubed minus 1. I want to prove that it has exactly one real root, and to do so, I'll start with the bijective function x, and manipulate it in multiple ways that preserve bijectivity until we reach p of x. And therefore, every real value is hit exactly once. In particular, p has exactly one real root. Plotting it on the complex plane, we remember that it has 2 other roots that are zeta away from it. We call the real root a, and zeta a equals b, and zeta b equals c. Then the other 9 roots are a complex conjugate pair, d and g. We pick the furthest right pair, and their zeta conjugates e and f, and h and I, plotted here. What a nice, pleasing chart. Anyway, we notice that a cubed, d cubed, and g cubed are the roots of the polynomial when we collapse x cubed into x, namely x cubed plus 3x squared plus 3x minus 1 equals 0. And so Vietta's formulas give us three immediate redundancies between a, d, and g, namely these three. But the final equation says a dg cubed equals 1, but d and g were chosen specifically for this to be real, so we can pop the cube off and just get a dg equals 1. We'll set those aside for now. Now here comes the fun part, step 3 of our agenda. Figure out what the Galois group actually does to our roots. It wasn't really noted for its own sake, but the Galois group of L over Q adjoins zeta 3 didn't fix any of the roots. So also, no two elements can take any root to the same other root. So starting with A, there is one Galois element going to any other root, so let's label them as such. That is, sigma A is the identity, sigma B takes A to B and fixes zeta 3, etc. An obvious first question is, what is sigma B? Well, it takes A to B, but what does it do to B? We can pull out the zeta and replace sigma B of A with B, and zeta B is C. So completing the 3 cycle, we know it takes A to B to C to A. And further note that it takes the thing inside the cube root, namely A cubed, to B cubed, which is also equal to A cubed. So it fixes the cube root of 2. And so we note that applying it to D cubed, which is made of things it fixes, leaves it alone. So sigma B of D is one of D, E, or F. Which one? Well, we can eliminate D immediately since it can't fix D. And if it were F, then we look at the third Vietta equality, ADG equals 1, which is certainly fixed by sigma B. And expanding the product and replacing what we assumed, we can cancel A and D from both sides to see that G would be fixed by sigma B. So that's impossible, and sigma B takes D to E. We can then fill in the rest of that 3 cycle in the same way and detect the 3 cycle involving G. So to visualize what's happening, we'll use these blocks, and sigma B acts by rotation to the right. And then as we learned in the previous example, complex conjugation always exists. It fixes A, swaps D and G, and swaps zeta and zeta squared. So as you would probably guess, it flips the red roots on the bottom with the blue roots on top, which on the blocks looks like this. We'll just note something about a Galois group with an index 2 subgroup. Applying complex conjugation also swaps group elements in and out of fixing zeta 3, so it swaps them in and out of this sigma A through sigma I set. The importance of this is that if we complex conjugate, then apply a sigma, then complex conjugate again, we get another sigma, and this fact will help us figure out the structure of the other sigmas. So sigma C is just sigma B squared, so the next one to ask about is sigma D. It takes A to D, and what completes the 3 cycle here? It can't be any of A through F, because we already have elements that take A through C to A, and D to D through F, so it has to be G, H, or I. And we go through the case elimination. If it were H, then we know where it takes everything by pulling out zetas. Then we compare complex conjugation, then sigma D, then complex conjugation, that acts like this on the roots, with 2 applications of sigma D and 2 applications of sigma B, which acts like this on the roots. They're both one of the sigmas since they both fix zeta 3, and in fact both send A to G, so they're both sigma G, but they aren't the same. So this case was bad, and we eliminate H. And in the same way, if it takes D to I, then we compare complex conjugation around sigma D, acting like this, with 2 applications of sigma D and 1 of sigma B, acting like this. Again, sends A to G and must be a sigma, but not equal, so we can scratch I too. So we conclude that sigma D is A to D to G to A. And looking at the structure more broadly, if we let A through I be vectors inside Z mod 3Z squared, then any sigma root acts by adding that root's vector to everything mod 3. And complex conjugation acts by negating every vector mod 3. We can use this model to write down equalities like conjugating a sigma root by complex conjugation, multiplying by complex conjugation on both sides of a sigma root, gives sigma sub that root's complex conjugate, but we have bigger fish to fry. The penultimate step in our plan, find the hidden redundancies which will help us eliminate non-Galois root transformations. So far, we haven't done much with our known redundancies, and for good reason. They're incomplete. If we had used them to write down the Galois group, we'd have too many Galois elements. We can ask what extra fake Galois elements we'd find, and what prevents them from being real Galois elements, and a quick counting argument gives us a hint. A can go to any of the 9 roots, and D has no real restriction except it can't have the same cubed image as A. That's 6 choices, and where G goes is fixed by keeping that final Vieta's equation true, for a total of 54 transformations. One example is A is fixed, D goes to zeta 3 times D, which is E, and G goes to zeta 3 squared times G, or I. We see the action of the blocks here. Clearly, this isn't any of the sigmas. It preserves the ordering of the first row, so it's not a complex conjugation, and it preserves all 3 equations. We're back in the same situation with the large group containing the smaller group. Remember the solution. Take an H-fixed polynomial that isn't G-fixed, apply all of G to it, and find the polynomial with those as its roots. As a starting example, we'll take A plus D plus G. This is certainly fixed by complex conjugation, and sigma D. And sigma B multiplies them all by zeta, thereby multiplying the whole sum by zeta. And so we can look at A plus D plus G cubed, which is fixed under all of the actual Galois group. But its image under the spurious Galois group includes 2 other elements. Expanding these out to see how similar they are, we note that they share 3 common terms with different powers of zeta in front of them. We can replace the first one in each from our Vieta knowledge, and we look at the inside of the multiplication by 3 in the rest of it as a better candidate. This is because if we expand this 3-term polynomial out, it actually becomes much simpler. That should look familiar to anyone who solved a cubic equation before, the usual way, not the one that I taught in the last video. Anyway, so now we have to compute uv and u cubed plus v cubed. Nothing to do except expand. We write down what 3uv equals, expand it out and collect terms, and replace terms with their equivalent Vieta factorizations. In the end, we get 9. We do the same thing for u cubed plus v cubed, whose difficulty is only increased by the number of terms, not by the complexity of the procedure. In the end, we expand it all out and end with 0. So collecting it all together, we get these 3 are roots of x cubed minus 9x, so they're 0 and plus or minus 3. There is an actual matchup 1-to-1 because these are specific complex numbers, but it doesn't matter, so we won't bother. And then step 5 of our agenda, we collect these redundancies into an answer. So remember our first redundancies. We were computing a plus d plus g cubed and its fake Galois conjugates. But now we're done. We can just plug in minus 3, 0, and 3 for those 3 things in parentheses, and learn that those 3 cubes are negative 6, 3, and 12. The obvious move is to take cube roots and then add. The d's and g's cancel because of the zetas, and dividing by 3, we get the same solution that the smarmy Olympiad student gave us. Again, I think it's worth it to look back at what we did. We were given a question whose answer in hindsight really doesn't look like it's much related, and we're told to build it from the ground up. And we were able to. I think the nicest part is near the end, where we ended up with the x cubed minus 9x polynomial. Again, that's kind of where it clicked into place. Up to that point, we were just kind of deducing based on the form of the right side that the question provided, but once we hit that point, it was more like, okay, yeah, there it is. We aren't wasting our time. It actually was able to be written in the way it suggested. Anyway, so these were 2 of my favorite examples of Galois theory in action. I hope you have a better idea how to go about using it if you ever need to. And on the screen right now, I've provided 3 exercises for you to solve with your newfound knowledge, the third harder and less routine than the first 2. You can solve them to the level of depth you like, but go ahead and post your answers in the comments. And like the video and subscribe to not miss out on any new uploads. Thanks for watching this far, and I'll see you next time.